So in this lecture, we're going to look at some examples of how we can use integration by parts, that's this formula over here on the left, to calculate some specific integrals. Right, so this is kind of the classic first example of how this is used, right? I want to find the integral of x e to the x dx. All right, so using this integration by parts method, I need to do two things. I need to split this original integrand here, including the dx, into two parts. One of those parts is going to be u, and the other part is going to be dv. Okay, so what I'm thinking when I'm making these choices, I know that my next step is going to be to calculate du, which means differentiating whatever I pick to be u. And over here, I need to find v, which is going to mean integrating whatever I choose to be in that dv spot. Right? So when you're making these choices, kind of what's driving my decision making is I want u to be something that I can differentiate easily, relatively easily. And I want dv to be something that I can integrate relatively easily. All right, so what I'm going to do here, I'm going to let u equal x. Okay, the reason I picked this, when I differentiate x, it's just 1. Right, so du is equal to dx. Right, so that term in a way, it kind of went away. Right, and it's often going to be a good thing if you can make that happen. So now let's see what's happening over the other side. Over here, this means dv must be everything that's left. It's got to be e to the x dx. And yeah, I know what the integral of that is. If I integrate both sides of this, the integral of dv is v, and the integral of e to the x dx is e to the x. All right, so let's put these parts into our formula and see what we end up with. The integral of x e to the x dx, those were my u and dv parts over there, is equal to, multiply u times v, x e to the x, minus the integral of v du. That's e to the x dx, and that I know what it is. You see now why it was helpful to make this particular choice? Right, when I differentiated x, it went away, and I can just keep integrating this part indefinitely. So now I get my answer. Right? This is x e to the x minus e to the x plus a constant, of course. And that's it. Right? That's my final result. That is the family of antiderivatives for that original integral. Okay, so I've got another one here for us to take a look at. And this one is, it's a little more interesting. Right? I'm going to do the same thing. What I see here, looking at the original, just kind of from a very high level, looking at this integral, I see I've got two things being multiplied together. Right? I've got x squared times the log of x. When I see two things being multiplied together, in my head, the first thing I go to is integration by parts. Now, there's no guarantee that integration by parts is going to work, right? That's just kind of a pointer to me saying, okay, let's see if we can make this method work first. All right, so let's get our parts. I need to know what u is, then I'll calculate du. And I need to know what v is, and then I'll calculate dv. Now, I really only have two choices here. I could, and I'm thinking about the v first. I can let v be x squared, or I can let v be the natural log of x. Well, I don't know what the integral of the natural log of x is yet. We're going to get there in a little bit. But I know what it is right now. So that would be a really poor choice for v because I can't integrate it. Right? So that kind of forces me, for lack of any other choice, to put x squared dx over here. And that leaves u to be the natural log of x. All right, well, if we differentiate the u part, du is equal to 1 over x dx. And if I integrate the v part, excuse me, this isn't v, that's dv. If I integrate this, this is x cubed. V is, I had them backwards. V is equal to x cubed over 3. Okay, so now let's go to our formula. The integral of x squared log of x is equal to u times v. That's x cubed over 3 times the log of x minus the integral of v du. So that's x cubed over 3 times 1 over x dx. You see, that's going to work out nice. That's going to be a monomial, right? I know how to do that. So this is, let me clean this up a little, 1/3 x cubed log of x minus, I'm going to bring that 1/3 out just to make my life a little easier, integral of x squared dx. All right, so now we'll do the integral. 1/3 x cubed log of x minus 1/3 times 1/3 x cubed. And now I'm going to go ahead, all the integrals are about to go away. So now I'm going to go ahead and put the constant here. And now just one more little bit of cleanup with that product. This is 1/3 x cubed ln of x minus 1/9 x cubed plus a constant. That's it. All the integrals are gone. I've simplified as much as I can. That's going to be my final answer. So now you've seen, right, a couple basic examples of how integration by parts works. Right? You get a feel for how you make these choices here. Right, so in the next lecture, we're going to look at 2 more interesting examples. Right, we'll see kind of some more interesting integrals that you can evaluate using this new technique.